You type a domain and get an IP in 20 milliseconds. That's not one lookup, it's 4 separate queries touching servers on 3 continents. One of them is lying to you. 98% of queries to the internet's root DNS servers are garbage. Broken implementations, misconfigured caching, devices looking up IP addresses as if they were domain names. And it gets worse. The system works by trust. Each server in the chain tells you where to go next, with zero cryptographic proof that it's telling the truth. For 2 decades, attackers raced that trust to inject fake answers. We'll show you how in a minute. So let's take it apart. Every packet, every flag, every step from your browser to the authoritative answer. The 5 actors in a DNS lookup. DNS resolution involves 5 distinct actors. Your application contains a stub resolver, a tiny library that knows how to format a query and send it. It talks to a recursive resolver, usually run by your ISP or a public service like Google or Cloudflare. The recursive resolver does the heavy lifting, querying root servers, TLD servers, and finally the authoritative name server that actually knows the answer. Every DNS resolver on the planet ships with a hard-coded list of 13 root server IP addresses. Not 13 machines, 13 names. Behind those 13 IP addresses sit 1,900 actual server instances distributed across 6 continents using Anycast routing. Froot operates 354 instances. Broot and groot each run 6. The 8-step query walk. Here's what happens when you look up www.example.com. Your stub resolver sends a query to the recursive resolver with the recursion desired flag set. The recursive resolver queries a root server asking for the .com TLD nameservers. Root responds with a referral, a list of TLD servers. The recursive resolver then queries the .com TLD server for example.com. The TLD replies with the authoritative name server addresses. The recursive resolver queries the authoritative server. The authoritative server responds with the actual A record. Finally, the recursive resolver caches the answer and returns it to your stub. You can watch this happen in real time. The command dig plus traceexample.com performs the walk manually, showing each delegation. First, it queries root and gets back all 13 root server names. Then, it follows the referral to the TLD servers. Then, the TLD referral to the authoritative name server. Finally, the authoritative answer. The protocol details. Every DNS message starts with a 12-byte header. It contains a transaction ID set by the client and echoed by the server so responses can be matched to requests. A flags field encodes query versus response, the operation code, recursion desired, recursion available, and the response code. Then 4 count fields for questions, answers, authority records, and additional records. Here's a real query captured with dig. The header shows operation code query, status no error, and an ID of 30,343. The flags are QR, RD, RA. QR means this is a response. RD means recursion desired. The client asked for recursive service. RA means recursion available. The server supports it. The RD bit is the switch. A stub resolver querying a caching server sets RD to 1, and the server does the walk for you. An authoritative server ignores IRD. It only answers questions about its own zones, so it sends an error if you ask for something else. When RD is set to 1, the client asks for recursive service and the server walks the entire tree. When RD is 0, the server replies only from its own cache or authority. If it doesn't know the answer, it returns a referral and the client must follow it manually. Stub resolvers always set RD to 1. Recursive resolvers send RD0 to authoritative servers because those servers don't recurse anyway. Caching and the traffic it kills. Recursive resolvers cache everything, both referrals and final answers. Once a resolver knows where .com's TLD servers live, it won't ask root again until that record's TTL expires. Once it knows example.com's authoritative servers, it won't ask the TLD again. Caching is why average DNS lookups take 20 to 120 milliseconds instead of seconds. This is why the root servers can survive. If caching didn't work, every DNS query on Earth would hit root first. Instead, a well-behaved resolver will almost never ask root for popular TLDs. It already knows where they are. But 75% of the queries root servers actually receive are from broken implementations that don't cache properly. 12.5% are for TLDs that don't exist. 7% are devices trying to look up IP addresses as if they were domain names. the constraint that shaped the internet. The original DNS spec limited UDP responses to 512 bytes. A root server response listing all 13 root names plus their IPv4 addresses had to fit in that packet. 13 was the maximum that would fit. 14 would overflow. That arbitrary packet size limit from 1987 still determines the fundamental architecture of the Internet's naming system today. The attack that exploited recursion. Here's the problem with DNS recursion. When a recursive resolver queries an authoritative server, it sends a request with a transaction ID and waits for a response with the matching ID. An attacker who can guess the ID can send a fake response before the real one arrives. If the fake arrives first, the resolver caches it. The Kaminsky attack works like this. The attacker queries the victim's recursive resolver for a random subdomain under the target, like random123.example.com. The resolver doesn't have it cached, so it asks the authoritative server. While that query is in flight, the attacker floods the resolver with fake responses, each claiming to be the answer, and each containing a malicious NS record for example.com itself. If any fake response guesses the correct transaction ID and source port before the real answer arrives, the resolver caches the poisoned NS record. Now every query for example.com goes to the attacker's server. The fix was source port randomization. Instead of using a fixed port for outbound queries, resolvers now pick a random port from a range of 64,000. Combined with the 16-bit transaction ID, that's 32 bits of entropy. The attack still works in theory, but the probability drops to 1 over n, where n is the port range size. But the real lesson is this. The attack exists because DNS was designed on trust, not cryptographic proof. The recursive resolver must believe that responses from TLD and authoritative servers are legitimate. DNSSEC finally adds signatures, but adoption is still incomplete. Quick recap. 4 things to remember. DNS recursive resolution is a walk through 4 server types: root, TLD, authoritative, and the recursive resolver that does the walking for you. The RD flag decides who does the work. Set it to 1 and the server recurses. Set it to 0 and you follow referrals yourself. Caching saves the internet. Resolvers cache both answers and referrals by TTL, so most queries never touch root. And the system was designed without cryptographic trust, which is why cache poisoning worked for 20 years until source port randomization and DNSSEC arrived. And here's the answer to the hook. One of those 4 servers, root, TLD, authoritative, or your recursive resolver, could be lying to you right now. Without DNSSEC validation, you have no way to know. You're trusting a chain where every link is an unsigned referral. That's DNS recursion. If this was useful, subscribe for more deep dives into the systems you use without thinking.